Okay, this is lecture 20, and we're kind of pivoting now to going to the rainfall runoff part of it, or the hydrology part. And we have been, from lecture 10 through lecture 19, on the open channel hydraulics portion of the course. Now we're pivoting into hydrology and hydrologic processes. And we're going to kind of do a general overview. This is a kind of a basic lecture. A couple things that you really need to be able to execute and understand well is delineation of a watershed, making sure that you can do that, and then that you understand flow duration analysis. When we talk about hydrologic processes, this is sort of encapsulating all that we're going to learn. So we're going to go have detailed lectures on this throughout the next several lectures periods, maybe 14 or so lectures. This stream flow duration analysis, I actually have an example problem that I downloaded from Oklahoma State University that is a tutorial, a very good one. And so you can actually, there's a data set that goes with it, and you can do some analysis and walk the tutorial and learn how to do flow duration analysis. Okay, so there's a few videos on the web that I recommend that you take 3 or 4 minutes each to watch. I think these are very informative, and you can kind of get a background for sort of hydrologic processes, following the water. These are put together. They're really nice, short little videos. So this is the hydrologic cycle. Not going to spend a lot of time on this because you can go through the video, but essentially what water we have on the earth is what we're going to have. They're not making any more of it. And so it's typically it's not typically, it's one of these, it's in part of the cycle. So it's either in the groundwater, it's on the surface, it's being evaporated, it's in the atmosphere, and it just keeps circulating back and forth. So what we have is what we have. We're not making any more, so we need to take good care of it. The various processes, there's infiltration, subsurface flow, surface runoff, spring flow and seepage, evaporation, as I mentioned, precipitation, interception, and that's like if you have vegetation on the landscape, that's the interception kind of part. It gets caught up in the leaf matter, potholes in the street. Those are all areas that can intercept and kind of store water, reservoirs, etc. There's evaporation from the land, and then there's transpiration. That transpiration is the process that happens when you have vegetation in bloom, where it can transpire vapor back up into the atmosphere. We call this typically in rainfall runoff processes evapotranspiration. It's the combination of the evaporation component and the transpiration. This is kind of a more narrated cycle of discussion and presentation on the water cycle, if you care to look at it. So if you look at the definition of hydrologic system, I kind of like this definition: a structure, volume, and space surrounded by a boundary that accepts water and other inputs, operates on them internally, and produces them as outputs. So we're going to delineate a watershed, and that's if we've got a system of streams and you've got a landscape here. That's the watershed is defined as if you have water droplets falling anywhere in this area that's delineated by this watershed, they will all eventually end up at the outlet. And so when we talk about a hydrologic system, we're talking about the infiltration, the groundwater component, as it fluxes out through the soil down into the deeper groundwater system, and or runs off on the hill slopes and down into the tributary streams. So examples of hydrologic systems: you've got the global hydrologic cycle, which we've talked about, and then we've got the precipitation rainfall runoff process in a watershed. So as I mentioned, and I've got a video example that I do of watershed delineation, but we're talking about the drainage divide, and these are all being able to delineate that, and what is encompassed inside that drainage divide is the watershed. We also know it as drainage basin. We also might call it catchment, but you'll hear me call it the watershed. And so when we look at characterizing watersheds and streams, there's a hierarchy of streams, and the stream order number is one of the ways that we describe streams. And so when we talk about a first order stream, we're talking about a stream that's very high up in the watershed that has no tributaries that contribute to it. These are typically intermittent streams. And so you can see up here, you've got two first order streams. When they come together and combine, they combine to form a second order stream. Now you'll notice that when I bring in another first order tributary to the second order stream, I still don't have a third order stream until I get down to this point where I've got two second order streams together, coming together and forming a third order stream. And so the larger the stream, the higher the order number. So if we look at, kind of a perspective on drainage basins, this is sort of just sort of a series of slides here that kind of talks about how drainage basins make up parts of bigger drainage basins, et cetera. So this is Friends Creek Drainage Basin near Decatur, Illinois. And so you can see it here. It comes out here at the outlet at the bottom to the right-hand corner. And so it's not very large. It's a few square miles at most, but basically from one end to the upper end, we're talking about probably about 10 miles or so. And from side to side, probably about 8 miles or so. So not very large, but then it becomes a part of a bigger watershed. And this is part of the Lake Decatur watershed of the Sangamon River. And so we're sitting here, and it's part of the state of Illinois, specifically right here. And so the Sangamon comes down through, and Friends Creek is right here in the blow up, and it contributes to the Sangamon. Well, if you look at the Sangamon, and it finally dumps out here into the Illinois River. And so the Sangamon, the Friends Creek, which is part of the Sangamon is part of a bigger watershed called the Illinois River, which dumps out down here just above Grafton, Illinois, just north of St. Louis, into the Mississippi River. So as you look at the Illinois watershed, then as part of the Mississippi watershed, you can see how big it drains. And you've got St. Louis right here. We're down here in Rolla, which is on this drainage basin divide here for the Merrimack. And so this Illinois River watershed, which has got the Sangamon, which has got Friends Creek, is part of the larger watershed, and it goes on down and drains to the Gulf of Mexico through New Orleans, and you can kind of see that. So it's just kind of a good perspective on drainage basins. They're sort of, you could think of them as a nested kind of situation. So if we switch into talking about atmospheric circulation, it's a very complex topic. And so through atmospheric circulation, that's how we get rainfall. That's how we get seasonal changes. That's how we get weather patterns. And so it's based on heating differences, based on latitude. We got the rotation of the Earth, and then we've got the distribution of the oceans, which are our source of our moisture as we get the evaporation off the process, off the ocean. And so when you look at the general atmospheric circulations, you've got the areas of latitude, and you end up, we're sort of in this part of the northern hemisphere where we get a lot of our weather comes from west to east, because we're in that westerlies part of the circulation patterns. You've got the trade winds section, which are the lower latitudes. Of course, here's the equator. And this general circulation is high up. It occurs in the troposphere, which is about 16 kilometers high at the equator. Of course, you hear a lot of discussion about the jet stream, and the jet stream does a lot to control our weather in terms of our temperature and kind of steering. And you know, when the jet stream in the United States dips south, we get more of a cooler pattern to our temperatures, and when it rises back to the north, we get that southern influence, and that moisture, or the air temperature warms up. And so global atmospheric circulation plays a large role in our weather. And so as you get this global circulation from our atmosphere, you also have ocean circulation, which plays a huge role as well, because as the ocean circulation occurs, you get warmer waters, you get cooler waters, etc. That plays a huge role on redistribution of heat, moisture, and ensuing weather. If you look at something called an atmospheric river, we have this in the western part of the United States. They used to call these pineapple expresses, but this is moisture that it's essentially brought on by the atmosphere, and it's a high moisture density as the atmosphere brings it up, and it can dump large amounts of rain in Arizona, California, and so you see a tremendous amount of moisture that can be moved up, and this graphic here is the Central Valley of California. So these atmospheric rivers provide an amazing amount of rain in a short period of time, so they can result in flooding and landslides and other kinds of phenomena. If we look at the examples of ocean impact on atmosphere and climate, I'm sure most of you have heard of El Nino, which is basically Eastern Pacific water off of the coast of United States and in the Eastern Pacific, that when it's in a warmer than usual pattern, we get what's called an El Nino cycle. And that has different influences and depending on where you're at. And typically when you see that in like the October to December time frame, when we're in an El Nino pattern, we're typically wetter here in the Midwest. And you can see areas that during an El Nino would be drier. And then during a La Nina, which is where it's cooler than normal Pacific moisture or Pacific temperature, you get different weather patterns from that as well. So when we look at rainfall, we're talking about, we're eventually after in this class is, what is the runoff from that rainfall? And so you have this landscape here, and when moisture in the form of rain or snowfall on it, you can, for when you have rainfall, it's going to, and it's enough that it exceeds the ability of the soil to infiltrate, it's going to run off into the receiving waters. And so this is a picture on my farm a few years ago, and we had a heavy rainstorm, and you can see these are areas in this pasture that are normally very dry, and it rained hard enough that we've actually got, you can see the water just flowing down. This is my lake here, upper end of my lake, and you can see water flowing off the hill slopes down into the intermittent little tributary streams there and down into the lake. And what this is called a hydrograph. So this is time on the x-axis and discharge on the y. And so what we've got is, if I had a stream gauge right in here, something that monitors the stream flow, both the water surface, the stage or the water surface elevation of the stream, and the discharge, this would be what it would look like after you have a rain event. You have this change of flow pattern. So this is the rainfall that's monitored in this hanging bar graph. And so it falls on the landscape and then runs off. And if I had a monitoring station down here in this stream, you could see how, that runoff would be taking effect. And so again, just defining this, we've got the streams, we've got the drainage divide here, and this is called the watershed. So I mentioned stream flow data. This is a kind of a graphic of sort of a cartoon of a stream gauge. And so we've got this stream here, and we've got this block structure. And inside it has got a, this is what we call a stilling well type of stream gauge. We have other ones that just have a sensor out in the water that determines how high the stream is. But this is monitoring through means of a data logger what the elevation of the stream is. And there's a float and a counterweight in here. And as the water here rises, the water in the well rises, and the float rises, and it goes up over the shaft encoder here, and it's able to encode that into an equivalent amount of elevation of water. And so you can see this antenna up here on the top of the stream gauge. This is broadcasting the data to our computer systems, and then we put it out on the web. And so we have the ability to continuously monitor the stage or the water surface elevation. Well, we don't want just stage. We want to know what the volumetric discharge rate is. We've been talking about the volumetric flow, and we call that Q. And then we measure that in the United States in cubic feet per second as the volumetric flow rate. And the way that we do that is we collect stage as a surrogate, and then during different times of the year, we go out and collect a volumetric discharge measurement so we can actually determine what the flow is, and we build what's called a rating curve. And this is a fairly simple rating curve. There are more complex ones where they loop, and there's various other factors that we have to take into consideration. But this is a plot of the stage on the y-axis and the discharge on the x-axis. And so if we monitor stage, we can go into the rating curve with the value of stage, come down here from stage and get what that corresponding flow is. So that's how we would use a rating curve. And this is how the data comes out. You can see that we've got time on the x-axis, and then we've got volumetric discharge here plotted in log space, but you can see what that looks like here as we put out into a web application where people can look and see what's going on. The last thing I want to cover during this lecture is something called flow duration analysis. And flow duration analysis is when you take the discharge from the gauging station and you come up with a representation of the relationship between magnitude and frequency of the flow. And so this magnitude can be a daily magnitude, a weekly, a monthly, or maybe even yearly. And so we collect this over time. Of course, you have to have enough of a time series to be able to do something with it. And this is a daily flow duration curve from a gauging station on the Salt Fork near St. Joseph, Illinois. So this is several years of data. And what you have here is plotted what's called the exceedance probability. So if you have an exceedance probability of 0.9, that's fairly high. That means that most everything below you is less than that, or I'm sorry, is I've got this backwards. Just let me back up here a second. So the exceedance probability means that if you've got a value of 0.9 or 90%, that means 90% of the flow values are above that value. And so here we've got a value of 10 CFS. This is a log plot here. So we've got 10 CFS. That's got about a 0.9 or a 90% probability, which means that 90% of the daily values of data are above 10 CFS. And you can see if we come down here to the median value at 50%, that's about, let's see if I go down here. So this is 20, 30, 40, that's about 50 CFS. So that says that 50% of the flows based on the data that's been collected over time are greater than 50 CFS. If I go down here to 10%, and I'm looking here, and that's about 250 CFS. So exceedance probability of 0.1 corresponds to 250 CFS. That means that 10% of the flows exceed that value. And you can see as we get higher and higher in terms of the discharge, that's a lower value of exceedance probability. The exceedance probability I want to mention is the 1 minus the percentile. So if we were to take that graph and do, kind of reorder it, we could look at the percentiles. And if you think of percentiles like in height or something, and we talk about somebody's height, if they're in the 99th percentile, that's pretty high in terms of, it's pretty tall. So there's not very many people. That means 99% of the people are shorter than them if you're in the 99th percentile, but that would be the 1% exceedance probability, right? So it's 1% of the population exceeds them in height, where the 99th percentile means that 99% of the people are less than their height. And so just to keep that in mind, because I may show you an exceedance probability plot for flow duration, or I might show you a percentile plot. You have to know the difference between the two. So when we're building a flow duration analysis, this is kind of the steps we'd go through, and you're going to go through this in the tutorial. But you're going to, first of all, decide the time interval of interest, daily, weekly, monthly, annual, etc. And then you're going to go get that flow data. and if we think about the daily data, we can go get that flow data, and we're going to order them ranked from largest to smallest. And we're going to assign a value, a rank of 1 to the largest value, and a rank of n, which is n would be the total number of data points you've got, to the smallest value. And we're going to then plot that data in terms of the rank. You know, basically where we have something called a plotting position. And so we're not just going to plot them from 1 to, let's say that I had 100 data points. We're not going to plot them 1 to 100. We're going to plot the plotting position is going to represent my percentile, okay? And again, the percentile is sort of the opposite of the exceedance probability. So but hang in here with me, and let's kind of work through this. So there's a couple different plotting positions you can use, and we can use the Weibull plotting position, which says that the P, or the probability or the percentile, is equal to I divided by n plus 1. And so I is their rank, and the n plus 1 is the denominator that we'd come up with that probability. And so I misspoke earlier when I said this is percentile, but this would be the exceedance probability. And so if I had the first rank that would be the highest value, you can see that out of 100, we'd have 1 divided by 101. So that would give me a probability that was fairly low. Or a percentile would be 1 minus that probability. And so I do that for all my data. I go from low to high, and for each data point, I give it a value of probability. And then I plot the probability versus the data point. And so this slide here, and again, I encourage you to go through the tutorial from the Oklahoma State University tutorial, and you can see that. This kind of describes the difference between exceedance probability or percent exceedance and the percentiles. So you could go through this on your own and kind of understand this, but it's kind of what I've just said. And the USGS, when you look at our data sites, we will rank our stream flow at a particular location where we're monitoring, and we'll put it in percentiles. And so when we think of, you know, 75% and above, we think of that as above normal stream flow. Between the 25th and the 75th percentile is normal. And when it's below 25th percentile, that would be below normal or drier. And so, yeah, it's just kind of good to know that, because you can look, when you look at our data sites, you'll know how we are ranking things. All right, so this is a quick example of the flow duration analysis. And we're just doing basically the annual flows here. And so I've taken this data, and I've just got basically 10 data points, and I'm sorry, 11 data points. So there's 11 years here, and I've ranked them from the highest March mean monthly to the lowest. And so you can see 1959 was the highest. I'm sorry, I haven't ranked them. Yes, I guess I have. And so we're ranking them based on, let's see, I gotta get this back here again. Sorry, wait, let's rewind there. So if I've got, this is my data, then I rank them. So you can see the highest rank is 1962 with a value of 287.7. So I ranked this 1962, it went up to here. The second highest was 1963 with a value of 245.5, on down to 1964, which has the lowest value, the March monthly mean stream flow, and that's 57.2. Now I'm going to use the Weibull plotting position, which says that P is equal to the rank value M divided by N plus 1. Well, we got the M, which is the rank. The N plus 1 is 11 plus 1. And so when I take the first rank for the 1962 data, that gives me a value of 1 divided by 11 plus 1. That gives me 0.083. And you can see I've written it down here. And so I went through this whole exercise, repeated this down through this example, and then I just simply plot the Weibull plotting position versus the stream flow value, and you can see what that looks like. And so this is the March monthly stream flow. This is the exceedance probability. It goes all the way from the lowest value down here. And I don't have that much data, obviously only 11 years of March stream flows. And so you can, but this kind of gives you an idea of what kind of the average monthly stream flow would be in March for this particular stream gauge. There's the flow duration curve for the daily period. And you can see this is the daily, this is the same site. And this was the month of March monthly. And there's various ways we do this. I've just given you a couple. I mean, there's various times, some kind of time increments that we use. And it's all depending on what we're trying to do with the data and trying to understand things. All right, there's a lot of uses for flow duration curves. We can, basically, as I've mentioned about the percentiles with the average flows being below average, above average, or normal. We use that to kind of give us an idea of drought. We can look at in-stream flow needs for habitat. We call it eco-flows. So what are the ecosystem that depend on the stream? What do they typically expect to have for this? And when we get below, when do they get stressed, et cetera. There's also estimation of stream flow at ungauged sites. We can do that as well, but that's kind of beyond the scope of what we want to do for the class. But there's various different reasons why we have flow duration curves.